Okay, so the first thing we're going to do in this section is a generic version of this problem for like arbitrary functions p and q. So we're looking at that y double prime plus p of x y prime plus q of x y equal to 0 and y1 a solution. And I'm going to start suppressing that of x notation. I'll just write y1, but remember that y1 is a function of x. So we'll assume y2 is equal to some function u that can depend on x times y1. Then we can go ahead and take the derivatives. y2 prime, and since u and y are functions of x, when I take their derivatives, I have to remember that I note their derivatives. So I would take like u prime is the derivative of u, or y1 prime is the derivative of y1. Because they're multiplied, I have to use a product rule. So if I took that u derivative, I leave y1 as it is, and then I'll leave u as it is and take my y1 derivative. And I do the same thing again to take the second derivative of y2. I've got u double prime, leave y1, plus leave u1, but take y1 prime. So that was just taking the derivative of the first term there. And then I'm going to apply a product rule to this second term. So derivative of u is u prime, and then I leave y1 the way it is. Or I leave u as it is, and I take the derivative of y1 prime, which becomes y1 double prime. And we can combine like terms here in the middle, u double prime y1, and then these two in the middle, u prime, y1 prime are the same, so it's just 2. I'm sorry, I think it's going to be crunched there, so I'm just writing it on the next line. You don't have to erase if you got started already. But it's 2u prime, y1 prime, plus that last term, u, y1 double prime. So that's y2, y2 prime, and y2 double prime. Now I want to plug that into the differential equation. So if I have 0 is equal to y double prime plus p of x y prime plus q of x times y, I want to plug in my y2. So that's going to give me of course it would move right as I start to erase. I'm going to plug in y2 double prime first thing. So u double prime y1 plus 2u prime y1 prime plus u y1 double prime. Then I've got p of x, and I want to, so I did y2 prime, plugged in that part because it matched what my y2 double prime was right there. Now I've got p times y2 prime, so I'm going to plug in this term in the middle. And I told you all I was going to suppress the of x notation to keep things a little cleaner in here. So I've got u prime y1 plus u y1 prime. And then I take q and I just plug in y2, which we can see up here is only u times y1. There's a lot going on here, but I know that eventually I'm going to want to try and get rid of the things that look like the derivative y double prime plus py prime plus qy prime, and I'm actually gonna have it turn out that the things where that happens are all the things that are multiplied by only u. And the reason it's nice is because then it makes all the only u's go away. So my next step here is just going to be to pull out all the terms that multiply. Sorry, I'm so bad at the camera. Pull out all the terms that only multiply by u, and then keep everything else on one side. So if something multiplies by u, I'm going to put it over here. Otherwise, I'm going to put it over here. So I've got u double prime y1, not normal u, plus 2u prime y1 prime, so it stays there. But my next term, u y1 double prime, I want to put it in this special category on the side. So I'll give myself this much space. Put it over there. Then next, I've got p u prime y1, and then p times u y1 prime. Since there's a regular u in it, I'd like to put it over here. And then lastly, I've got this q u y1, and it includes a q, or a u, so I will put it over here. And I gave myself a bit too much space, but that's fine. Just so you know, when you do specific problems, it's actually a little bit easier to see which terms go where. So don't worry if that selecting by u was confusing, and definitely don't commit that rule to memory, because you probably won't need it. But everything that I had before, I'm just going to leave the same, and then I'm going to pull out that u that's in all those terms, since that's the thing they have in common. And then I'm going to leave everything else inside those square brackets. And what's helpful here is now I have inside those square brackets y1 double prime plus py1 prime plus qy1. And that's the ODE on the left side of the equation for y1. Since y1 is a solution, that means when I plug it in, the equation has to be true, or all that stuff has to be equal to 0. So right now I can just say all of that is going to go away. So all that I'm left with are all those terms that I put out front to start. Suddenly it got a lot simpler. And our next step is going to be to group like terms using u's. So I want to have u second derivatives and u first derivatives all together. So u double prime times y1 stays the way it is. But then I'm going to have u prime is multiplied by 2y1 prime in this term, and then py1 prime in that term. And this is where the changing the order part happens in the problem, which we are still in the setup category, but we are so close to moving on. So we're going to set w equal to u prime and w prime equal to u double prime. If we do that, this problem becomes 0 is equal to w prime times y1 plus w times 2y1 prime plus py1. That's a first order differential equation, so we're going to be able to solve it. We can start writing it in a way that makes that a bit more clear. y1 dw dx plus 2y1 prime plus py1 w. And hopefully you're starting to see that since I'm not really sure what p and y are, of my first order methods, I'm feeling pretty good about separable compared to linear. In this section, you'll usually be able to also use linear. Actually, you will always be able to use linear. I can't think of a reason you wouldn't. We're going to do separable because I like it more. But this is a separable equation, and we're going to solve it as such. So we rearrange our separable equation. to get, I'm going to move the square bracket part over to the side first. Negative 2y1 prime plus py1 times w is equal to y1 dw dx. And I'm thinking about getting the x's on one side, the w's on the other. So that's negative 2y1 prime plus py1 over y1 times dx is dw over w. The reason why I'm putting the y's and the p's on the dx side is because even though I've suppressed the notation, y1 and p are both functions of x. Y1 is not a function of y or w or u. So then at this point, hopefully we can see that it's separable and we just have to integrate both sides. So we're going to get that the integral of this thing, not sure how I would do it yet, but I'm going to write it down anyhow, is equal to the integral of dw over w. If I separate out the fraction on that left side, I start to see a way to make this a little bit easier on myself. Dx minus integral p dx. So if that step that I just took wouldn't naturally occur to you, that's totally fine. It's understandable. But the thing is that it's a useful way to split things up because this was a whole mess I didn't know how to integrate, but there is a special relationship that will allow me to integrate that I've underlined. So I'm just going to note that a chain rule tells us that natural log of some function has derivative f prime over f. So I can take this antiderivative and know it's just natural log of the function, or in this case, y1. Then after we integrate, we're going to get that that first integral, y1 prime over y1, becomes just natural log y1. So I've got my y1 prime over y1 should turn back into natural log y1 when I take the antiderivative. Since I don't know p, I wouldn't know how to integrate it right now. But a constant would come out of my integrals, and then all that is equal to, on the right side, natural log w, which we're quite happy taking that integral after doing separable equations for so long. I'm going to pause here. The second half of the equation is going to be kind of solving for w and then undoing everything we did to get back to the original solution we wanted.